Hi everyone. So this is a little screencast about electricity and electrocution and Ohm's law. So we talked about safety in your home with the electrical system and what fuses and circuit breakers do. So you may be wondering, could you be electrocuted at home? And the answer is possibly, but certainly not likely. This electricity is very safe, relatively few accidents each year to do that. But to help answer that question, I actually just want to show you this video. So let me just go ahead and play that now. And I want you to look for these questions. So if you haven't printed out the slides, you should go back and you'll want these because the answers to these questions will go in your homework. So you want to pay attention to the video.
Welcome to Life Noggin. Electricity has allowed for some great things in our world, but it can also be pretty dangerous. In the United States alone, a little under 100 people a year are killed from being electrocuted in the workforce, and about another 60 electrocutions occur from consumer products like power tools and lighting equipment. Electrocution is defined as when a person or animal is killed by electricity or an electric shock. But how exactly does electricity hurt someone? Well, to understand that, let's take a step back and see how electricity is measured. Volts and amperes, or amps, are typically ways engineers and scientists describe the electrical phenomena of the world. Amperes measure current flow, or how much electricity charge flows through a point per unit of time. Electron flow is what typically causes harm to a person through tissue or nervous system damage. When flowing through the body in ways they aren't typically supposed to, electrons can cause damage inside a person. These include the burning of bodily tissues or interfering with essential electrical signals, like the ones that cause the heart to beat. Under certain conditions, a person's muscles will tense and clench, sometimes even preventing them from letting go of the current source. The Occupational Safety and Health Administration gives some guidelines on just how dangerous certain amperages are. Currents around 1 milliamp can cause tingling sensations, while currents above 75 milliamps can potentially cause ventricular fibrillation, which may lead to death. Severe tissue and organ burns typically begin at currents above 1,500 milliamps. But you have to take into account more than just the amperage when seeing how the current of an electrical source will harm a person. Theoretically, a small current can flow into one hand directly through the heart and out the other hand and cause a person to die. At the same time, an extremely large current from a lightning bolt could hit a person and only cause bodily burns if it simply travels through the skin and not further inside a person. Certain body parts are also more susceptible to electric damage than others, with someone's inner organs having far less resistance than their outer skin. Wet skin also has way less resistance than dry skin. This is why people are at a far greater risk of electrocution when water is involved. So obviously high amounts of electricity going through you are pretty bad. But is there ever anything that can make a little electric kiss be a good thing? All my Left 4 Dead fans know that there is. The defibrillator. Modern day defibrillators can vary quite a bit from what you see in video games, but they are basically devices that deliver a therapeutic dose of electrical energy to a person's heart in order to treat urgent medical conditions like sudden cardiac arrest. Sudden cardiac arrest is a condition where a person's heart abruptly stops beating, usually caused by ventricular fibrillation. Without the use of things like CPR and a defibrillator, sudden cardiac arrest usually leads to a person's death. See, electricity can be a dangerous thing, but it can also save your life. So, have you ever been electrocuted? Have you or anyone you've known?
By the letter I in the equation. Voltage is V and resistance is R. So I is equal to V over R, or if you multiply both sides by R, you get V is equal to I times R. So those are mathematically equivalent. And there's one more representation if you want to solve it for R, but you guys can figure that out. So remember, I is equal to current, and that is measured in amps or amperes. V is the voltage, so as we saw earlier this week, so the more voltage there is, the more current that wants to flow. So that's measured in volts. And R is resistance, and I don't know if we ever did the units for resistance. So resistance is what's trying to oppose, it's an obstacle to the flow. Okay, so that is measured in units called ohms. And ohms, in terms of the symbol for an ohm, you'll get Greek letter omega. V is volts, A is amps, so that's not a big thing. So if you look at Ohm's law and the current, so basically you have two competing things in the circuit. So you have the voltage, which is trying to push current through, and you have the resistance, which is an obstacle to that current. So how much current you actually get is the relationship between those two. So you can look at this and you can see if we keep the resistance the same and the voltage keeps going up, then the current's going to keep going up. If you keep the voltage the same and increase the resistance, then the overall amount of current is going to go down. So that's consistent with what we have seen before. So a couple quick examples here. Say we have a 9-volt battery connected to a bulb that has 3 ohms of resistance, and we want to know the current through the circuit. Okay, so we know that the current is equal to the voltage over the resistance, and so we have a 9-volt battery and 3 ohms of resistance. So that means we are going to get 3 amps of current going through that circuit. If we have the voltage in the outlets of our houses, and this is true in basically everybody's houses, the voltage is about 120 volts. The toaster is plugged in and draws 10 amps of current, and we want to know what is the resistance of the toaster. So if we do it kind of systematically here, so I'm looking at this and going V is equal to 120 volts. Amps of current, so that's I is equal to 10 amps, and so we want to know what the resistance is. Okay, so actually if we use the Ohm's law in this form, it can help you keep from making some simple math mistakes. So 120 is going to go in for the voltage, the current is 10, and I'm looking for R, so that means R is 120 over 10. Like dividing by 10, that's easy. That's equal to 12 ohms of resistance. So it's a pretty easy equation to use. Now when we talk about circuits and resistance, so we can have different, like in the circuit construction, we talked about series and parallel circuits with bulbs, but sometimes we want to talk just specifically about things that are called resistors. So if you've ever taken apart anything electronic and looked at a circuit board, you'll probably find some things that look like these. Okay, you may not see the long wire sticking out, but you'll see some of these on there, and those are resistors, and their only job in a circuit is to be an obstacle to the flow of current, to have resistance. And I don't want to go into detail about what they're used for, but they're there. The little stripes on there is a code to determine how much resistance they have. So they're usually pretty small, so it's hard to print numbers on there. So they've come up with this code with the different stripes and different colors to show you what they are. So when we draw a circuit diagram, so we haven't really drawn circuit diagrams. A resistor is symbolized by this zigzag line. Okay, and so if we want the equivalent resistance, so let's say that we have 2 or 3 resistors in series, and we saw the other day that adding bulbs in series increases resistance. So let's say that we have so I'm going to draw this freehand, which is usually kind of sloppy. Okay, so let's say we have a 1 ohm and a 2 ohm and a 3 ohm resistor. And what I want to know is, what I mean by equivalent resistance is, what's the one resistor I could replace these 3 with that would have the same resistance. So if I want to take out these three, and I only had one resistor that was the same obstacle to the flow as these three in series together like this, what would it be? And it turns out it's really simple. So in this case it would be 6 ohms. Okay, and if you're looking at it, that's equivalent to the equivalent resistance is equal to the sum of the individual resistances. I'm going to put this little dot 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 here because we could have any number of resistors in series. The equivalent resistance is what you get when you just add them up. So this would be like R1, R2, and R3, and this would be REQ, or the equivalent resistance. So we have a rule for series. We just add up the resistances. Okay, next we're going to look at, well actually we'll do another example. So in this case we want to find the equivalent resistance and the current through the circuit. So common type of question. Okay, so the first thing we're going to do is we're going to find REQ, and that's going to equal 5 plus 4 plus 7, which I believe would be 16 ohms. So what we mean by that is now that when we have a circuit, and by the way, this is something new, I think, this symbol represents a battery. So the long line and the short line, that represents a battery. So this is like having a battery in terms of resistance to the flow. This is like having our 48 volt battery connected to a 16 ohm resistor. Okay, and now we want to find the current. So the voltage is equal to 48 volts. The resistance is equal to 16 ohms. And so the current is what we're looking for. And we have two forms of Ohm's law. You should get the same answer whichever one you start with. So I'll use the voltage over the resistance. So we've got 48 over 16, which I believe is equal to 3. So 3 amps. So this current will have this circuit will have 3 amps of current traveling through this. So if you think back to the FET thing, you would see current flowing, and if you put out your little meter and put it on there, you would see 3 amps of current there. So those are series resistors. Now in parallel, things are a little different. So if you remember the other day, we saw that adding things in parallel actually lower resistance. Okay, so if we start, for example, with a 12 ohm resistor, so let's say we have 12 ohms of resistance, all the current would have to go through there. Okay, now let's take that 12 ohm resistor and put another 12 ohm resistor in parallel to it. So remember, in parallel there's a fork in the road, there's a choice. So now we have a 12 ohm resistor and another 12 ohm resistor. Well, if you think about it, now we've made it twice as easy. So my analogy for this is going to the grocery store. If there's only one checkout lane open and everybody has to go through that, there's going to be a high resistance to the flow. Not many people are getting through the checkout line. If you open up another checkout line, then more people can flow. You're going to get more current, okay, in that example. And since we've added that same lane, same resistance, it's actually twice as easy. So in this case, the equivalent resistance, we've cut the resistance in half by doubling the number of lanes. So REQ would be 6 ohms. So just follow along with me here. I'm kind of making an argument. Okay. Now if we had the 12, our original 12 ohm resistor, and now we're going to add up, we're going to open up 2 more checkout lanes, or we're going to have 2 checkout lanes added to that. So now I've added I have 3 lanes, so it's going to be 1/3 as much resistance as it was before. Okay, so Req here would equal 4 ohms, and so on. So the idea is if you have resistors in parallel and they are all the same resistance, and that's where we have to be careful, they all have to be the exact same resistance, then the equivalent is just the value of one resistor and you divide by the total number of branches you have. So this is 12 over 2, this one's 12 over 3. If we had 6 resistors in parallel, being real sloppy here, but if these were all 12 ohm resistors all throughout 12 ohms, then Req would equal 12 over 6, which would be 2 ohms. Okay, so that is kind of nice reasoning, but we want to be a little more formal with that, and this only works if they're all the same resistance, and in life they're not all the same resistance all the time. So there is a rule about 4 resistors in parallel, okay, and so that formula looks like this. So we have 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus, and we'll use the dot dot dot. Okay, so let me do a quick example. So if we go back to our 3 resistors, our 3 12 ohm resistors in parallel, so if we are looking at our 3 12 ohm resistors in parallel, so in this case 1 over the equivalent resistance would equal 1 over 12 plus 1 over 12 plus 1 over 12. Okay, and so we've got fractions, we're adding fractions, don't panic, fractions are not scary. Okay, so we have to have a common denominator, which we do, so you just add across the top. So 1/12 plus 1/12 plus 1/12 is equal to 3/12. Okay, but now that is equal to 1 over the equivalent resistance. So I want just the equivalent resistance, I don't want 1 over that. So I need to flip it over. Fancy word is of course reciprocate. So if I flip that over, then I need to flip this one over. So the equivalent resistance is 12 over 3, which is equal to 4 ohms, which is what we reasoned it would be a couple slides ago. Okay, so we have a formula for parallel, and a formula for series, okay, which we had on the previous slide. Alright, so let's do an example here. So now we have 2 resistors that are not the same. Okay, so let's find the equivalent resistor here, resistance. So we're going to take 1 over Req is equal to 1 over 6 plus 1 over 3. Okay, so it looks like our common denominator would be 6. So I would have 1/6, and then I could add on, for our common denominator 6, I'd multiply top and bottom by 2. So 1/3 is equal to 2/6. And now that you have the common denominator, you can add, so that's 3 over 6. And so that means Req, we want to flip that over, is 6 over 3, which is equal to 2 ohms. Okay, so that means this circuit, in terms of the obstacle to the flow of current having a 6 and a 3 in parallel would be the same thing as having a single 2 ohm resistor. Okay, and now we can do the current. Current is equal to V over R. So I've got 24 volts over 2 ohms of resistance. That'd be 12 amps of current going through there. So we're going to have 12 amps of current flowing through there and coming back to the battery. Okay, just one more slide. Okay, so this circuit, I was getting lazy and didn't want to take the time, so I'm going to draw this out by hand. So we're going to have, first one, we're going to have 3 resistors. We'll have a 24 volt battery, and then we will have 6 ohms, 4 ohms, and 2 ohms. So these are in series because there's only one path. Remember, series means there's only one path. So REQ is going to be 6 plus 4 plus 2. So that's 12 ohms. And so I always like to redraw. It's not mandatory. So if we've got 24 volts, 12 ohms, then the current is going to be equal to V over R. So 24 over 12 is 2 amps. Okay. Our next circuit, we will have, let's say we have a 50 volt battery. And here we're going to have 3 resistors in parallel. Again, my zigzags are very sloppy. And let's say each one of those is 30 ohms. Okay, so these are in parallel because they're forks in the road. Okay. So the current flowing around can go through any one of these 3 resistors. So that makes it parallel. So 1 over REQ, we're using this law, is equal to 1 over 30 plus 1 over 30 plus 1 over 30. So that's equal to 3 over 30. So then we get REQ is equal to 30 over 3, which is equal to 10 ohms. So again, in terms of, I could take out these 3 30s in parallel and replace them with a 10 ohm resistor, and in terms of the resistance of the circuit, it would be the same. So 50 volts, 10 ohms, and so the current is equal to V over R. So that's going to equal 50 over 10. So I is equal to 5 amps of current. And for the last one, then let's do our .24 volt battery. Two resistors. Wow, that was really horrible. 6 ohms and 3 ohms. Okay, again, ask yourself if those are in series or parallel. There's a fork in the road, so that's parallel. So we're going to use the 1 over REQ rule. That's 1 over 6 plus 1 over 3. I think we just did this one recently. Like 1 over 6 common denominator is 6. Multiply top and bottom by 2 to get to the common denominator. So that's 2 over 6 equals 3 over 6. So flip it over at the end. Req is equal to 6 over 3, which is equal to 2 ohms. And so that means, again, this is like having a 24 volt battery and a 2 ohm resistor. And so the current is equal to the voltage over the resistance. So that's going to equal 24 over 2. So this would mean we'd have 12 amps of current. So there you go, some pretty basic circuit problems. So your assignment will be just using these two formulas, and it'll have a little bit of the some questions from that video. So that's it for Ohm's law and electrocution.